Welcome, everyone. Good afternoon. My name is Ben. Welcome to our session today about clinical quality language deep dive. Our speaker is Bryn Rhodes from Smile Digital Health, and the floor is yours.
All right, thank you. I have a lot of slides, like way too many, so I'm going to go through these really quick. We had the Let's Build session for this yesterday, and we got through quite a bit of detail there. So a lot of those slides I'm going to skip over. So I'm Bryn Rhodes. I'm Director of Standard Strategy at Smile Digital Health. I apparently don't know how to mute my own laptop. Is that, no, like I muted it and it's still coming out. Fair enough. It's just distracting to hear myself talk to myself. All right. All right, so learning objectives, we're going to understand general importance and architecture of CQL, basic constructs and capabilities, understand how CQL accesses data. We're going to learn some CQL queries and identify current tools and programs using CQL. Okay, we're going to go through fundamentals and background first. So knowledge representation standards, that's really what CQL is about. If you look around when we started this 10, almost 15 years ago now, you have things like Arden syntax, guideline elements model, Jello, HQMF, knowledge artifact specification. These are just in the medical space. There are lots of other kind of rule formats like PRR, Rule ML. So this is my favorite XKCD. 927. I'm sure you all know it. That is, we're well aware, but what do we really need? Like, what do we actually need at the end of the day? Create and share computable clinical knowledge. We want a formalism that's clinician and domain expert friendly. It's clinically focused. It's unambiguous. We can use it to clearly and precisely share content. And it's platform and technology independent, and it has to be sufficiently expressive. A lot of these things get into really complex territory, and we need a language that's powerful enough to do everything we need to be able to do. So we took a look at that set of requirements, and there wasn't anything that completely covered that set without extensively retrofitting. If you want to use SQL, for example, you have to build in terminology and temporal support and all sorts of clinically ubiquitous constructs that you would have to standardize anyway. So we built a language from the ground up that includes those capabilities as first-class elements. Second is the clinical quality framework. This is the effort and initiative that looked across decision support and quality measurement. Historically, they were using very different stacks, and there's no reason for that. They're two sides of the same coin. And so we harmonized around a common metadata standard, a common data model standard, and common expression logic. This bottom part, the common expression logic standard, is clinical quality language. And this is just history. I'm just going to go, this is in here. If you're interested and you care, this is where all of the standards that went into what's now the clinical reasoning module in FHIR, clinical quality language, and CDS hooks, how they evolved over time. All right, so the design. When we talk about interoperability, there are different types of interoperability. We typically, with FHIR, we're looking at data interoperability, but there's also knowledge interoperability. And within that, it's a continuum. It's not discrete. And so they have lexical interoperability. That just means we're sharing the same symbols, A, B, and we mean the same thing by those on both sides. Syntactic builds on lexical interoperability to say we're sharing the same structures. When I talk about a procedure, it looks like this, and on your side, it looks like the same. And then semantic interoperability builds on that to say the code element of the procedure means the same thing when it has this value on both sides. And that semantic interoperability is where we start to get into knowledge interoperability. I can't really build on any of these layers until I have the layer below. And so the next one is logical interoperability. Once I'm sharing the same structures and the same semantics in those structures, then I can start to share expressions about those structures. And that's logical interoperability. And process interoperability builds on that. Once I have, I don't know. Yep, no, it's still there. I don't know how to turn it off. It's this weird gremlin in the back of my computer that's like mimicking me. So process interoperability builds on that to say I've got, now that I can share expressions, I can start to share workflows and actual processes. CQL focuses on logical interoperability and assumes and asserts semantic interoperability from the layers below. Any luck?
Maybe if they're in a browser website with the Zoom open, or?
No, it's just the Zoom.
You're not also in Move On by any chance?
No. Yeah.
Next to the microphone symbol on your screen, if that's what's being shared, there's a little pull down, and you should be able to disconnect computer audio from that. See if that, do you have like a disconnect computer audio somewhere on there?
Okay, how about that? Now am I not over there? Yeah. Perfect. Thank you. I do know how to mute. I mean, it's muted. It just isn't.
I don't know anything about FHIR, but I understand.
Fair enough. All right, so those are types of interoperability, and what we're focused on with CQL is this logical interoperability. We want to be able to share expressions. That's what we care about. So how do we do that? When we talk about sharing logic, we allow the model and the terms to evolve independently. The model is the structure, the terms are the semantics, and the logic is the behavior or expressions that we want to share on top of that. The architecture of CQL, at the highest level, it's an authoring language, text, just like any other kind of language that you would expect. In the middle layer there is ELM. That's a machine-friendly rendering. It's an abstract syntax tree if you're a language nerd. The idea there is that it's easier to build language processing applications at the ELM level, at a machine-friendly level. And when you're processing text languages, you have to get to that level anyway before you start actually playing with it and doing things like type inference and translation and compiling. And so we share at that level. This is the same model as Java. They compile down to bytecode, and then you share the bytecode, and you do processing applications at the bytecode level. And some of those processing applications are to actually run it or to translate it, to transpile it to JavaScript. We just saw a presentation about transpiling it to C#. You could translate it to SQL and run it as a query against a database management system. That depends on your environment, but what we care about is the ability to share unambiguously the expression written in CQL, and so that's what that architecture is about. So CQL is a high-level standard designed to enable point-to-point sharing of executable clinical knowledge. It provides a clinically focused, author-friendly, human-readable language. It's currently published as mixed normative trial use HL7 ANSI standard. At that link, it's pretty easy to remember. So language preliminaries. So the characteristics, one, it's a conceptual language. It's not going to tell you exactly how these things run. It's going to let you describe what you want to have happen, not how you want to do it. It's a functional language. You can't change values ever. There's no storage, there's no update. You're reading data only. It's deterministic. Every time you run an expression with the same inputs, you're going to get the same outputs. No matter what that expression is of CQL, it's a deterministic language. It's clinical, so there are constructs in it that support clinical use cases, most notably the interval support for temporal expressions and terminology support. And it is a query language. It's not a programming language. It's a query language. We don't write code, we write expressions. It's not imperative. So the elements here, the lexical elements, these are the kind of tokens that that these expressions are based on. So we have white space, we have comments, We have literals. So literals are the actual values, like 120 days. We have symbols like less than or equal to. We have keywords like define and where. And we have identifiers like inpatient encounters. The language constructs then are built up of those white space elements. So the literals, the identifiers, operators, so things like days or less before, functions like age and years at, and then I can use those to build up expressions like where encounter relevant period during measurement period, and I can use those to then build up queries like encounter with major diagnosis, with major depressive disorder diagnosis called encounter 1, and so we'll get into those a little later as well. Just a note, it is case sensitive. Strings are case sensitive for equality, but case insensitive for equivalence. There's a tilde operator where you can use. Codes are typically case sensitive, but note that that might be a function of the defining code system. Some code systems have case insensitive codes in them, and that would be respected by the terminology service. And note that UCOM units are case sensitive. UCOM can be used in case sensitive and case insensitive flavors, and we mandate in the spec you have to use case sensitive UCOM with CQL. All right, types and values. For overall, we support simple values like strings, numbers, dates, structured values. So these are values with named elements in them, like FHIR resources are structured values. Intervals are ranges of values, lists of values, and then we have a choice type, which is the same kind of construct that you see in a FHIR choice. Simple types we support are booleans, integers, decimals, strings, dates, date times, and times. I'm going through a lot of this really quickly. How many were at the Let's Build? I mean, some of you are familiar. So if you were at the Let's Build, there's an exercises that walks you through these. So most of this is the same kind of things you would expect in the standard expression languages. So I'm going to go through it really quickly because what I want to get to is queries, right? So missing information, how many of you are familiar with SQL and how SQL deals with nulls, right? This is exactly the same as that. It's anti-null SQL handling, which means null is not a value. It is the absence of a value. And in CQL, it can be read, I don't know, right? If an expression results in null, it means I don't know. Is that value greater than 10? I don't know what that value is, so I don't know whether that value is greater than 10. And so that's a really important piece of logic, and we use that a lot. If you need to ask if it is null, there are null testing predicates, and if you need to get a value out of a list of values, you can say coalesce. CQL also supports conversions, both implicit and explicit. There are very few implicit conversions defined, less than SQL, less than most languages nowadays. That's because we want to make sure that you really do mean, like if you add 1 and John, you're not going to get an answer. The translator will tell you, I don't know how to add integers and strings. So there are very few actual implicit conversions, and they're only allowed when it's the case that you could never lose information by going through that conversion. We have type testing and casting. The model does support type systems that have inheritance, and so you can use things like is and as to say if a value is of some type. There's strict casting and loose casting. Cast as will actually throw a runtime error, whereas a loose cast will just give you a null. And then choice types, and in particular, the translator will tell you or will allow you to treat a value as any of the types that it might be. So if you have a choice type that says this is an integer, a decimal, a string, or a quantity, if you treat it like those types, the translator will allow you to do so. But if you ask it to say, is it true, for example, in this case, that's going to be a translator error because Boolean is not one of the allowed choice types. So the translator will let you treat the value like any of the choices. Okay, and feel free to stop me if you have any questions. but I'm going to keep going. All right. Operators. So we support standard set of comparison operators. We have relative comparisons, just like you'd expect. The call out here is equality versus equivalence. We have equal, that's strict equality on structured values. That means it has the same values for each element that has a value. And then equivalence, in general, won't propagate nulls, where equal, in general, will. So equal will give you, like if you ask 1 equals null, that's going to be null. I don't know. But equivalent is going to say, yeah, no, that's not true. All right. We also support date comparison at precision levels, right? So I can say not only this date is equal to that, but I can ask things like, is this the same year as that? Or is this greater than at the year or month precision? And so it lets me choose the level of precision I want to take that date comparison down to. That's super important in temporal logic. It also supports date arithmetic, so I can add durations to date values. So I can say things like today minus a year. I can add minutes. This even works on partials. So if I say the year 2014 plus 24 months, I'm going to get the year 2016. A note about calendar durations versus UCOM units. Calendar durations for years and months in CQL are variable durations, right? They're calendar, so they're based on that. In UCOM, they're not, right? In UCOM, an annum is 365.25 days. And so you have to watch out for this. We do this in the implicit conversion between FHIR and CQL values, because it's almost always the case in FHIR data that if you say 1 annum, what you mean is 1 year. But just watch out for that, and note that the equivalent will work there. But if you really mean annum, convert it to seconds and do your math in seconds. But that's what you're doing if you really mean it. Okay. Duration and difference. We support duration, which is whole periods between 2 dates, and difference, which is boundaries crossed. Right? So there's use cases for both, especially with clinical data. You might want to care. You care about when midnight is, right? So there are use cases for both those. So we support duration and difference both. We also have conditional operations, if, and then a selected case and a conditional case. If you're familiar with SQL, this is exactly the same syntax as the case expression in CQL or in SQL. It's very similar to SQL. There's a reason for that, right? It's intended to be easily translatable to SQL. All right. We also have intervals and lists. I'm going to go through these pretty quickly, but basically we support the mathematical notation for intervals. So square brackets and parentheses for open and closed endpoints on your intervals. So that shouldn't be a surprise to anybody. Support a complete set of operators for comparing intervals. So you can ask if this interval is includes or overlaps or meets before all of the operators. There are also support for timing phrases. So you can ask if a given interval starts before the start of, right? So you can access the endpoints of the intervals and use those in timing phrases. So I can say, does it start 3 days before the start of, 3 days or more before the start of? So I can start talking about intervals before and after. And I can also do within. So I can ask if it starts within a range. All of those get translated to just pure interval functions down in the ELM. But the intent here is to support as natural language phrasing as possible for all the different kinds of timing phrases you want to use. Then we also support list values. Those are just curly braces with comma delimited lists. And a bunch of functions on lists, including unions, intersect, accept, membership, all of the things you would expect to be able to do with lists, including some important ones about lists of intervals. So lists of intervals, like if you're calculating, say, medication reconciliation, you want to know the total duration of a set of intervals, you can ask for the collapse, and that will give you the minimum set of covering intervals for a set of intervals. That's a really common calculation in medication adherence. All right, so now clinical data. So if we're looking at a CQL library, you have kind of header sections at the top and then expression and function definitions at the bottom. Header lets you say you have to start with a library. Then you can say, I'm using this model. I'm referencing these libraries, so I can talk about any number of other libraries I want to bring in. I can declare code system, value set, and code declarations that let me use local names for those terminologies within this library. I can declare parameters. I can declare a context. It's typically patient, but that might be organization or location, depending on what you want to do. What that context means, we'll get into a little bit more. And then you have expressions and functions. So libraries can be versioned. They can reference any number of other libraries. That library version is opaque to CQL. And you can also give a library a name within your library. So if you reference another library, you can give it an alias, and then you use that alias to talk about it in your library qualifiers are required when you're referencing components of a library, so that it's clear when you're calling out that you're calling some external function. All right, models. I can use CQL with any model. I just need a model info. That model info gives you the structures that are available. So we make model infos available for quality data model and for all the different versions of FHIR, as well as being able to generate model infos that are based on profile definitions. So for US Core and QI Core, we ship model info for those as well. And that lets you talk about the extensions and slices that are defined in the profiles as first-class elements. So each data model is described with the model info, and it also specifies a primary code path for retrievable types. So if you have a condition, the primary code path is typically code, and that when you retrieve means that your terminology target will reference that code. We'll look at that a bit more. It also specifies a patient type, so it knows how to, like the age in years at function, for example, knows how to get to the birth date for the patient through that information in the model info. The model info is not required by ELM. It's only a translator time function. The translator is just needs information about the type system that it's going to. Here's an example. This is actually QDM, the diagnosis class in QDM that has onset, abatement, severity, and so on. So it's a very simple nested type structure for models. FHIR model info provides resource structures. The translator has built-in support for several ballot versions as well as all the main versions. And there's a CQL to FHIR type mapping. That mapping is important. A FHIR.boolean is not the same as a CQL boolean, because a FHIR.boolean has a value and an ID and extensions, right? None of those things exist on a CQL boolean. And so there's a library called FHIR helpers that lets you get to and from those things easily. All right, let's talk about terminology. So if you look at the terminology section of a library, it supports code systems, value sets, codes, and concepts. CQL does not define code systems and value sets. You can't author code systems and value sets in CQL. You can only reference them. They're just, all it does is give the CQL environment the name of that code system or value set that you want to use. It's up to a terminology server to give you that content. The code, this looks very similar to a coding in FHIR. That's not an accident. And concept, this looks very similar to a codable concept in FHIR. Again, that's not an accident. But I can declare those things in CQL so that I have a local name for them when I'm talking about them in my library. And terminology operators, I've only got 10 minutes. Are you kidding me? Okay. All right, we're going to speed up. You use string valued codes. The slides are out there, and there's an exercises thing that you can go through. Like all of this is in the CQL spec. Use string valued codes only for required bindings. That's the only time that it makes sense to use an actual string, because otherwise you're doing a system independent conversion, and that's just wrong. So use inline value set construction only for required bindings, right? So when I say o.status in final and amended, that's only valid because of that required binding. Use in to test for value set membership. So if o.value is in current smoker. Use tilde to test for code equivalence. Now, this is not terminological equivalence. Like, you're not asking a terminology server to do like semantic comparison here. This is just an equivalence. It compares only the code and system, ignoring display and version. And so use code equality, the actual equal on code values, only if you really mean it, right? You really want the system and display and version and code to all be the same for those. There are cases for it, but typically you want the tilde. All right, data access. So conceptual versus physical data access. If I look at this expression, smoking status observation, this is giving me observations in the tobacco smoking status value set where the status is final or amended. This evaluation requires those observations in order to run. If it's not given those, you can't really get an evaluation of this. So when we talk about getting that evaluation, we're talking about a request, and then the response is going to give us the results of that evaluation. So how that actually happens depends on where it runs and what it has access to. So there's the simple case of in-process access, where the engine that's running this expression has direct access to the data that it needs to run on, and we just ask for a request. This is like an SQL query. So if I run the query, it runs in the database, and it gives me the result. That's the first case. Then there's service-based, right, where the engine is actually accessing the data through a service like a FHIR REST endpoint. And so it's going to take that and turn it into a query against that FHIR service and get the data back. Or it might access data in files on the local system, right? From the perspective of the evaluation, we don't really care. All we care is this kind of interface about a provider. And a provider interface is a way that the engine actually gets data. And the provider may be in a database or a RESTful API, or it may be a local values or files. Either way, it's all going to happen the same way, and it's going to happen by accessing clinical data. So we recognize that in clinical data, there's statements that are organized into different types, like patient had a routine checkup, or patient was administered an antibiotic. So different kinds of clinical statements. Within these different types, different kinds of statements can be represented with codes from code systems. So with an encounter, for example, you had a patient had a routine checkup, or the patient was admitted to the ED. Those codes describing different kinds of statements can then be grouped into value sets. So a patient had a routine checkup, there's typically 10 or 15 values that mean routine checkup for what I care about, right? And so I typically bundle those into a value set, and then I use the terminology target of the retrieve to say, give me encounters in the inpatient value set. And that retrieve results only in the highlighted encounters because they have codes that match the inpatient value set. So the retrieve is like a where on the primary code path of that type. In fact, that's another way to say it. So another retrieval example, the primary code path in the model info, if you don't specify it, it will use the primary code path from the model info. So in this case, encounter will use code. But if you want to change that, you can say encounter performed diagnosis in, and you can actually tell it where you want that to go. So then a word about context. The context is model defined, but it typically includes patient and the system defined unfiltered, right? So you can write unfiltered CQL, but then it's like you're writing against the entire database. Typically we see context patient, which means that your expression is from the perspective of a single patient. So you can think of it as unfiltered, you're accessing all the encounters, but if you're in patient, then you're accessing only the encounters for a specific patient. And it's up to the data access layer to tell you about that. All right, almost there. I'm going to fly through these queries. The CQL query structure, what we care about here is this alias over here. So any expression followed by a name means you're giving that expression that name, and you're introducing a query context. This is kind of like the select in SQL and the from clause, where you name the things in the from clause. You're just introducing a query with that alias, and then you can have the clauses. The clauses are lets with and withouts, wheres and sorts. That retrieve can then be filtered with a where. So you introduce that alias, and then you can say where encounter relevant period during the measurement period. You can do with and without. The with is a semi-join, basically. It just lets you say, give me encounters that have a relationship to laboratories, for example. This one says, give me encounters that had a laboratory test performed during the encounter. You're still going to get just the list of encounters, but it's only going to be those encounters that had laboratory results during the encounter. Does that make sense?
Yeah, I'm trying to figure out the difference between such that and
Such that is so that we can distinguish between the where and the such that. But such that is a Boolean that only applies to the with.
okay.
Yeah?
So, okay. Conceptually they're the same.
Yep. Yep. And then you can say without, right? I can take that same thing, and these are conceptually the same as writing it with an exists, right? It's just so common in logic that we have a shorthand for it. Then you can do return. This is like the select list in an SQL query. I can say, give me only these elements. Typically, if you omit the return, it's just going to be whatever type the source is. And then I can order with the sort. The order is based on the actual output. So you don't use the alias names in the sort clause because you're out of the query construct by that time. You're at the very end. All right. So that was queries. Any questions? All right. Because now I want to do a more advanced query. So this is appropriate warfarin therapy. This is from one of the ECQM measures. This is patients who received warfarin and parenteral anticoagulation for 5 or more days with an INR greater than or equal to 2 prior to discontinuation of parenteral therapy, or 5 or more days with an INR less than 2 and discharged on overlap therapy, or less than 5 days and discharged on overlap therapy. So we have these concepts within here. We're talking about encounters, we're talking about warfarin therapy, we're talking about parenteral therapy, and there are several different relationships between each of those things. So the way to break this down is first we establish the source data for encounters. So here we're going to say we've got inpatient encounters. Those are encounters with a class in the inpatient with a class code of inpatient encounter, where the status is completed or in progress. Warfarin administrations, that's a medication administration of warfarin, where the status is completed. Parenteral anticoagulant administrations, and then INR observations. So those are laboratory result observations where the status is final. So that's kind of the set of things that we need to talk about. Then the problem here, what we've looked at so far is just single source queries. Give me encounters where or observations where. What happens when I need to, like in this case, I need to talk about patients who received warfarin and parenteral anticoagulation and that warfarin therapy all at the same time. So how do I do that? So CQL defines a from clause. The from clause can have a single source in it, which is the default, and that's what you're typically doing. But you can introduce any number of sources with the from clause. So say from those data elements that I just set up. So from inpatient encounters, comma, warfarin administrations, comma, parenteral anticoagulant administrations. And what that is, just like in SQL, it's a cross join. And so what you're going to get out is all the possible combinations of all those values. So that's step one, to say, now I can talk about all of those things. I brought them all into the query context. And then I give them aliases, E, W, and P. So the first thing then is to bring in the limitation that we only want warfarin and parenteral administrations that started during the encounter. So I take the W effective and make sure it starts during the E dot period, and the parenteral anticoagulant and make sure that starts during the E dot period, right? So now that's limiting to only those encounters and warfarin and parenteral anticoagulant administrations that are at the same time. Next, we want to make sure those two therapies overlap by at least 5 days. So the duration in days of the warfarin effective intersected with the parenteral effective, the overlap of those, is now 5. Note that that's just the integer 5 because I asked for duration in days, right? And finally, we want to make sure that the INR was greater than or equal to 2 prior to stopping parental anticoagulation. And so what we do then is say that the last INR observation that's on or after the start of the parenteral and on or before the end of that parenteral, so that INR is during that parenteral therapy, and sort that by the effective. So we take the most recent INR in that set, and we say the value of that is greater than or equal to 2. So that's the first of the criteria, but there are 2 other ones that talk about exactly those same values, right? The last INR and the overlapping. So what we do is pull those overlap duration, that calculation for duration in days of the effective of the warfarin intersected with the parenteral anticoagulant effective, and the ending INR, so that last INR observation. We take both of those and we say so now I can talk about overlap duration as that expression and ending INR as that expression. And then I can say the effective and the overlap duration is greater than or equal to 5, and the ending INR is greater than or equal to 2. Right? So that's that same first criteria, but now expressed using the lets. Now that I have those lets, I can express those other 2 criteria by just saying the first bit or the overlapping duration is greater than 5 and the ending INR is less than 2, and it overlaps the end of the encounter, or the overlap duration is less than 5 and the parenteral effective overlaps. So I can reuse those same expressions to get that criteria. All right, that's what I wanted to get through. All right, so what did we learn? Hopefully understanding general importance in architecture, some basic CQL operators, and how you can use CQL to write some fairly complex queries. Contact me during DevDays here, and now we're to Q&A. Oh, and there's a survey. So.
Thank you, Bryn. Is there any questions?
Yes, thank you for your presentation. I have a question regarding extensions. With CQL, how easy or difficult is it to find certain extensions and to use them in your queries?
So if you're using pure FHIR, then what the model info will say is you have an extensions element, and then you can access the extensions in the same way that you do in any language. What we do in the model info for profile informed, we call it profile informed authoring. What we do in the CQL in that model info is for the extensions, and we do this with slice definitions as well. So like if you have blood pressure and it's got systolic and diastolic. We take the names of those extensions and slices and make them first class elements. So if you're looking at a US core patient, for example, it's got an ethnicity extension, and so then the patient type in US core, like if you say using US core, the patient has an ethnicity. So you can just say patient.ethnicity. What that does in the ELM is actually output that as patient.extension where URL is blah, blah, blah. And so to a consuming system, it looks just like FHIR and behaves in that way, and they don't have to actually know or care that it was done that way. But to an author reading the CQL, it looks like patient.ethnicity, first class element. So it's super easy, but it wasn't easy to get to that it's super easy point.
Any other question? Oh.
Thanks, yeah, great. I'll rewatch it at 0.75 speed. But at one point you mentioned that the CQL is intentionally modeled after, for instance, SQL to be convertible. If you wanted to actually convert it to SQL, is that relatively possible, or is it no, go to the Elm first anyway, and then translate Elm into whatever you would need?
You would typically go to the Elm first.
Okay.
You don't have to. You could start and try. We have a .NET CQL to ELM, or
No. Yeah,
ELM to
to
SQL
okay.
translator. It's actually from the, ELM predates CQL. ELM came first in the Healthy Decisions project a whole long time ago. And in that project, we actually took a VMR-based CDS measure for chlamydia screening and translated it to SQL using OMOP. And so there's a framework in .NET that will read ELM and translate it to SQL.
Nice.
You would typically, I mean, you could start with just the CQL, but even in ELM, the constructs are very SQL-ish, and
Okay.
intentionally so that you can,
Awesome.
like, there's a query and you can do that translation.
Awesome. Thank you.
Yep.
Thanks a lot for the talk. It's actually a follow-up on that SQL question. So, yeah, many of the constructs that you described is very similar to SQL. And then when you say there is an ELM to SQL framework, so my question was basically, once you try to do it in SQL, then you need to assume a schema for how your data is represented. For example, you could just have like bare JSON as your data representation. There is a completely different SQL, or you can have like SQL on FHIR or something else, which is a completely different. Is there, and I understand that at CQL level, you try to be not opinionated about the representation of the schema. But when, for those kind of approaches that they want to go from Elm to SQL, what schema do they assume, or what are your opinions about what schema should be assumed?
So we actually, in that framework, added the transformation to model at the same time. So it's not only translating the expression, it's translating the model, because we couldn't assume what the structure would be. And there are, like, you can do both the transformations at the same time, but there are some like pretty important restrictions about what kinds of things you can do. We don't have a good answer there because there's not a rendering, right? I mean, it's kind of with the extensions and the fact that they're recursive and you never really know what extensions you're going to see. There's really not a good answer for what the schema should be. It's almost kind of use case specific. And so we're trying to support the use of different kinds. It would typically be driven by the set of profiles you care about, where you take the profiles and that drives your schema. And then because you're written against a set of profiles, then at least you have a bound on what that schema needs to look like. So in getting to those kinds of analytic transformations, there's probably going to need to be some agreement beforehand, before those analytics can really be shared.
I have a follow-up question to the follow-up question.
Perfect.
So from the translation from Elm to SQL, how does that handle terminology? Like, does it just take the code system, display, and version and put that into SQL, or how does that work?
It just assumed a value set structure and just did it as a join. But it kind of glossed over versioning. So that's a detail that would need to be addressed. If you really do it properly, you would need you'd either have to do it with a function and a terminology server, which would probably kill your performance, or you would have to have like a version specific terminology table for every code system, and yeah, it would be. But yeah, in that, we just assumed like a value set table, right? So there was some simplification there. That's an area that would need to be like fully worked out.
All right, I think that's it for questions. Thank you for joining us, and thank you, Bryn.
Yep.